Let's see. All right. Oh, they actually replaced the batteries up here. That's kind of cool. This is the first time I've seen the mic back be like uncharged. Okay, yeah, so what a beautiful day, isn't it? Nice shady day. But thank you guys for coming. Today is the 16th lecture. Yeah, 16th lecture. So we're making good progress. Less than 10 lectures. We have 10 lectures after this. So yeah, we're making good progress towards the end of the year. So today we started our discussion of deep neural networks by discussing multi-layer perceptrons, multi-layer networks basically. Last lecture, so today we're just going to talk about convolutional neural networks. These are the type of networks that you commonly see when we start processing images for reasons that will become very obvious later. So yeah, hopefully for most of you, well, I'm going to leave that thought aside. But in this lecture, we're going to discuss convolutional neural networks, discuss the attributes of convolutional layers, and the advantages of CNNs with respect to the parameters and spatial information within the data. Okay? Yeah, please. That way. Oh, sorry, I forgot to mention. MB Convert, I was using a new library today, and MB Convert was just behaving badly with it. So that's where I was all morning. I was trying to make the stupid Jupyter MB Convert working with the OpenCV library. So I'm gonna upload the actual. I think I know the problem, but it's gonna require me creating a whole new environment. So I'm gonna fix that later today. But I did upload the code. So you could look at the actual Jupyter notebook. But hopefully also we have the slides here. Yeah, sorry about that. I didn't realize it would pose a challenge until it was too late. I should have tried it last night. All right, so let's just refresh our memory with regards to multi-layer networks. And let's recall. We have a multi-layer network. It takes in an input, which is some vector of real numbers, and it's put through a series of k layers. And each layer is composed of a multiplication of the weight matrix according and accounting for a bias term, right? Even though we don't specifically specify it anymore, the bias term is almost always present because that little bias equals true term, usually people put it on. And it does make a difference when you're actually training the networks. So let a particular weight matrix let WK denote a weight matrix at K. Then we have basically this complex function here, where X is multiplied by the first layer, then is put through an activation function, then that is multiplied by a second layer, activation function, all the way down the line, then we'll multiply by the k minus 2 layer, activation function, k minus 1 layer, activation function, k layer, activation function, right? So what's important that we discussed last time is that every layer needs to be separated by a nonlinear activation function. This is to stop the layers from combining with each other and forming just like one large set of slopes, right? Because if these activation functions weren't here, then what you would essentially have would be constant matrix times 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 x, which is a linear function, right? All those constants reduce into one constant, and you get a linear function that way. We don't want that, so the special thing we have to do with multi-layer networks is simply insert in activation functions in between the layers to get a final output. And I should mention that not each of these activation functions. Oh man, this is going to be hard. These activation functions don't have to be the same after every layer. In fact, they frequently aren't. There's a whole slew of literature, especially I want to say around the mid-2010s, which tried to argue one like sort of permutation of activation functions is better than the other. I don't think there's any sort of theoretical backing behind any of that. It always depends on the data set. But I want to really emphasize these sorts of things, these activation functions are different. It is up to the user to decide what your activation function should be. So for a k-layer MLP, we have a k-1 activation functions. And so each of the layers with the activation function becomes the hidden layer. And what else? First layer has a matrix. So remember that the hidden layers, all they're really doing, all the hidden layer is doing is transforming a input of size D to a input, an input of size N to a output of size D, right? That's really all each layer is doing. It takes in an input, size D, transforms it into another size N. And sometimes each subsequent layers makes the input smaller and smaller and smaller out to the output. Sometimes it makes it larger. Maybe you have something convex. You have a convex network. Doesn't really matter. Again, up to the user. But that's all each hidden layer is doing. Just taking something small, making it big, or taking something big, making it small. And it does that often enough. You get a complex function that basically could match the outputs, the classification output of most data sets. So in this case, all this is to say that the depth of a multi-layer network is simply the number of layers. That makes sense. But multi-layer networks also have a width, which generally is defined by the size of the largest hidden layer. That's generally what people use as the width. It's kind of like O notation, asymptotic bound. Largest width, like largest layer defines the width. Okay, so last time we saw multi-layer networks are useful because they could give you a nonlinear boundary where you initially only had linear boundaries available to you with linear regression or with logistic regression, either way. You only had that linear boundary straight line available to you. These multi-layer networks, what's nice is that they combine all these boundaries together to get a new super boundary. So they combine linear boundaries together to get nonlinear boundaries, to combine those nonlinear boundaries together to get even more nonlinear boundaries. And after you do that a couple times, you're able to match this sort of classification of the data set perfectly, hopefully. And we also saw towards the end of last lecture that the multi-layer network achieve a near perfect training accuracy on the fashion MNIST data set with a fairly strong validation accuracy, up to 80%. Why is the validation accuracy only 80%? Let me ask you guys. Why couldn't I get, why doesn't the validation accuracy match the training accuracy? Yeah, please, Ben.
Well, at a certain point, it'll start to like overfit, and then we'll see patterns in the specific training set that isn't generalized.
Yeah, that's a pretty good way to say it. So the important thing to remember the difference between the training set and the validation set is that the training set is the stuff we're actually giving to the network, the stuff that the network is changing itself to match, right? And the validation set is something that we're keeping aside just to give us, the programmer, an unbiased evaluation of the network, right? And then then there's the test set, which is something that we compared in our network with other people that we don't even have access to, right? But the difference between training and validation is that training, the network is trying to match. Validation, the network is not trying to match. And no matter what you do, there's going to be some difference between the training and validation. validation sets. There's going to be some minor things that are different. Maybe there's slightly more dogs than cats in the training set than in the validation set. So if the network keeps training on that, it's going to learn, it's going to sort of, it's going to overfit on that thing. It's going to make itself more specialized towards dogs and less specialized towards cats. And then once you get to the validation set, that's not ideal, right? So that's the reason why. So that's exactly, so the term we use for that is exactly overfitting. Basically, the network keeps trying to perfectly predict the training set, which is great, but at a certain point, it comes to the detriment of the validation set. So either you plateau, either your validation accuracy plateaus, or worse, your validation accuracy could actually decrease. Actually, that might be a good thing maybe next time. That would make a good homework problem, to see the validation accuracy decrease. I got to think more about that. Yeah, you have to find just the right data set. But anyway, so in the last lecture, we saw basically the validation accuracy plateau around 80%. Makes sense. And the training accuracy become near perfect. So one thing that's interesting is that in theory, the network isn't necessarily looking at there's no spatial relationship between the pixels in the network, right? When we take the image in, we basically convert the image into a single vector, and then we pass that vector into the network, and then every single hidden perceptron is connected to every single pixel in the picture, and then every single perceptron is connected to every single pixel. So therefore, it doesn't view any pixels as close together or not close together, right? Because it's just connected to all the pixels. Every single hidden element is connected to all the pixels. So what does it really mean for the network? What does it really mean for the network for a particular picture to be a picture of pants? You know? That's sort of weird. So because it has no spatial awareness, it means we could do something it means we could mess around with the network a bit. So one thing we could do is we could scramble the images. We could scramble the images. We have our old-fashioned MNIST data set here. And the other thing, we have a new fashion MNIST data set, but we'll call it scramble fashion MNIST data set. And all it does is that it permutes the data set in some random manner. Okay? It basically, we have a permutation. Remember, it's a 26 by 26 data set. So we're just gonna, it's 784 pixels. So we're just gonna basically reorder those 700, find a reordering of those 784 pixels. We're gonna keep that reordering consistent among all the images. We can't just have a different scramble for every single images. But we're gonna have the same scramble for every single image, okay? So what we do is basically, we initialize a new scramble data set, and where we had a picture of pants before, we now have something. We have a whole thing. We have a permutation of that image, okay? So the question is, can the network still learn this? To us, this is garbage, right? To us, this is garbage because our human eyes aren't looking at actual pixel values or anything like that. Our human eyes are looking for edges, they're looking for shapes, etc., right? So permuting the images like this would completely throws us off. But it turns out with a multi-layer perceptron, it's not so bad. So we do the same thing that we've done before 100 different times. We have instead of 2 layers, we're going to do a 3-layer MLP now. We have the same, we have the linear, we have the input layer, the first fully connected layer, second fully connected layer, and an output layer. And we connect them all like so. Then we do the same old training loop that we've done 100 different times, which is get batches from the training loader, set the gradient to 0, make some predictions, calculate the loss, calculate the gradients, and iterate on the parameters in the model. All that is pretty simple, and then we simply record the loss, and we record the loss and accuracy for the sake of our own sake of graphs. And then so we do the same thing that we've done 100 times before. By the way, isn't it nice that the thing that we've done 100 times before is reduced to 5 lines? Pretty great, right? Thank you, PyTorch. And also we have a helper function. This is just calculates the accuracy for a model on a given input data and given labels. So we do that, and then we plot. And when we plot, we see that the training accuracy, no, you're not going to, OK. I could go, there we go. We see that the training accuracy for the model trained on the original images, and trained on the original images and evaluated on the original images, non-permuted method, the training accuracy goes to 100%, and the validation accuracy goes to roughly 80%. Pretty much the same as if you scrambled the model. Now, with the scrambled model, remember, we're still training the scrambled model on scrambled images. And so, like, we're training the scrambled model on scrambled images, comparing apples and apples. But same pattern. Training accuracy goes to 100%. Validation accuracy goes to roughly 80%. Yes, Caleb?
Are these scrambled images, are they all scrambled in the same way, or are they just completely random?
They're all scrambled in the same way. Okay. So that's the key. So just going back here. So right from the beginning in the scrambled data set, yep, there we go. We calculate a random permutation that we store with the object for all the images, okay? So if we didn't do that, so that's a good question. What do we think would happen if we didn't do that? If every image had a different scramble, would the model learn anything? Is there no information that the model could abuse? It'll find something. Any thoughts? Yeah.
Maybe like how many light-colored squares there are versus dark, or well, pixels.
Yeah, I think it would learn maybe that, you know, like shirts are correlated with higher pixel density, things like that. So it might not get a completely random accuracy. So it will get something above random. That might be a good experiment. Someone, if they want to do this at home, take the code, try just a random permutation per image, and post on Piazza what you get. I would like to see the number. So I don't think it would go down to 10%, right? There are 10 classes. So 10 classes, you would expect just a terrible model getting it correct, getting accuracy at 10%, right? You wouldn't expect anything lower. Let me see. As I'm saying that, I'm wondering, do we start off? Yeah, we start off at 18%, at 20, well, that's, yeah, 25%, yeah. Yeah, so you wouldn't expect anything lower. You wouldn't expect the model to get anything lower than 10%. But there probably is some correlation. There probably is some correlation because the only thing you would have if you completely scramble each image and add a random scramble for each image, all you would know is that X pixels had the value of 1. Y pixels had the value of 0.8, like Z pixels had the value of 0.6, and so on, right? So there's probably some information there, but it's probably not. You'll probably not get very, very far with that information. So, but that's a good question. Excellent question. I was wondering about that too, but I just ran out of time to actually make a test out of it. So the most important thing, though, is that the scramble still works. If the image is scrambled, even though our pattern recognition brains can't recognize the images. The model can. The model can work with a scrambled image, work with permuted images to get some good accuracy. Now, so that's kind of cool. Of course, let's go back slides. Of course, so, oh, by the way, I forgot to say, the word for this is permutation invariance. That's what, when a model is able to process a piece of data, even if the data is permuted in some fashion, that's what it's called, permutation invariant. And that comes up with especially with language processing models often. Because, you know, a lot of, like, bag of words is permutation invariant. When you toss everything into a bag and just get features based off how many times each word appears in a paper, that's what permutation invariant means. So it does come up. So that's something. So that's a term that's useful and will come up later. Of course, the other thing we could look at is, could one model, for instance, could the model trained on the standard data set get anything from the model from the shuffle? Could the model trained on standard data set evaluate the shuffle data set, and vice versa, right? Could the shuffle data set evaluate the standard data? Could the shuffled model evaluate? Could the model trained on the shuffle data set be evaluated on the standard data set? And so the short answer is no, right? So right here I'm evaluating them on the test portions of the corpuses. So again, with the tests we get accuracies in the 80-ish% range, and evaluating the standard model on the shuffle data set gives us an accuracy of 9%. Evaluating the shuffle data set on evaluating the shuffle model on the standard data set gives us an accuracy of 10%, right? So effectively random. Effectively random. So not great. And actually, as I'm doing this, we don't need that. That was debugging. Okay, so the major question here is this a good thing? Is permutation invariance a good thing? On one hand, you know, I mean, it doesn't hurt, right? Like, imagine your video camera screwed up, and like it's just sending, like the channels, the bus channels are all crisscrossed or whatever. It's sending information in a weird way, but it's sending information in a weird way consistently. Could be useful. But seems something wrong, right? What's wrong with this? Yeah, please, Patrick.
If it's permutation invariant, that means it's not making use of any information in the correct or original method.
Yeah. It's not. It's basically.
We're not making use of any special information.
It's pointing to the fact. It's suggesting that it's not efficient, right? It's suggesting that it's basically a brute force at that point, right? And that's not a great thing to be when you're an engineer. When you're a physicist and you're just trying to prove something works, man, the brute force is your best buddy. But when you're an engineer and you need something to work well, because you need to go home eventually, this isn't great. And it's not great especially because, you know, the model, the thing we're working on here, the number of pixels, it's what, 26 by 26? We have 384 pixels, and then we have a whole bunch of weights in layer 1. We have 128 hidden layers, so we multiply that by 128. We have 128 biases. That gives us 100,000 parameters just for the first layer between the input and the first hidden layer output. And then for the second hidden layer, we have 128 hidden layers that go into 64 hidden layers, hidden perceptrons. So plus 64 biases, another 8,000 parameters. And then for the third hidden layer, we have 10 outputs, 64 perceptrons, 10 outputs. So we get another 650 parameters. So we have 100,000 parameters, right? So it's not a terrible amount of parameters. It's not an obscene amount of parameters. LLMs have trillions of parameters, and they're pretty great. But big is only good if it performs a big task well. And the thing is that, again, as we left off last lecture, if the image size goes up to 256 by 256, the number of parameters explodes to 4 million, right? And that's 4 billion, sorry. The number of parameters explodes up to 4 billion. So that's not good. That's not good. The number of parameters, 4 billion parameters to just classify some images is a terrible, 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 terrible thing. Even if you have permutation and variance, there's not a lot that you could justify that, right? There's no point in taxing your graphics card that much if all you need to do is classify images into 10 categories. And that's sort of the issue, right? You're not making good use of the parameters. There are other issues, of course. There are other issues where, the model is permutation and variant, but it also is slightly stupid. And so there are other downfalls to the model. Specifically, since we're not using spatial information, it's getting very used to, especially since we're not using relative spatial information. We are using absolute spatial information, right? Basically the middle pixel in the image will always appear at the same point in the vector, right? So even though we're not detecting an edge in the picture, we are still giving it some sort of spatial information. We are telling it that the middle pixel in this image is white. The leftmost pixel in this image is black. That sort of thing. Now, not an awful thing, but when the position information that you're giving to the model is always absolute, basically you're giving the model this pixel, this absolute position is this value. The issue is that if the position changes a little bit, the model screws up, right? The model becomes very sensitive to the change in the position. So to demonstrate that, I came up with a little motivating example, similar to the shuffle data set, except instead of permuting the image, all I'm doing is shifting the image slightly to the right and slightly down, right? Easy, not too bad. So I created this. So we created a new class, standard fashion MNIST data set, and we fill it out same as always. We download the data from Torch Vision. We fill out this the underscore len function, and when we do the get item function, all we really do is shift the data. All we really do is we shift this image data to the right and to down by some set values when we created some set values and values we passed in when we first created the data set. Okay? So for instance, when we first create this shifted fashion on this data set object, I'm telling it shift the image over by 2 pixels and down by 0 pixels. Okay? So I'm literally doing a 2 pixel shift to the right. And what will happen here, I download the data, but when the rest of my model calls, retrieves the data, this data set will return the image where the X start is moved over slightly, and the rest of the image is just black, is zeroed. Okay, this is what's known as zero padded data. Basically, you're shifting something over, and the extra bit that's added in, it's all equal to 0. So pretty simple data set. I'm not doing anything too special here. So again, just to visualize it, we have a set of pants, and then we have a set of pants slightly to the right, off center, right? This is a thing of the MNIST data set that I think all the images are pretty much centered, which really shouldn't matter much, but you'll see in a minute if it does. Okay, so that's all that data set is. That's all the shifted data set is. I'm just shifting the image over by a couple pixels. The columns that get shifted out of the range basically get discarded, and the columns that get shifted into the range, I just fill with zeros, which in general shouldn't affect the images too much. I will concede that there might be a case, especially for instance in this case, if I was to shift it down, part of the pants might get cut off, but it shouldn't affect the model too bad, right? It wouldn't affect us. So if we take the shifted data set and evaluate it on the standard model, the model that was trained using the same the fashion non-permuted data set, the fashion MNIST data set. If we just evaluate that model on the shifted data set, on the shifted images, the accuracy drops from 80% to 39%. So that's a pretty big drop-off. And it's not that big of a difference. That's the issue. It's not that big of a difference. All this is a little bit of shift. It's 2 pixels. It's not like I'm completely altering the images. But the issue is that the model is used to seeing things centered. And when something is slightly off center, it freaks out, right? It doesn't completely fall apart, but this is a pretty big drop-off, and it's worrying, right? So new things are required, right? What's really we need is a way that instead of saying that, okay, this is a pant because this pixel needs to be white, this pixel needs to be white, the center pixel should be black, et cetera, we want it to be able to see that, okay, this is a pant because there's a line like this, and there's a line like this, and a line like this, and a line like this, and there's some outline that forms the general pant shape. We want to basically process our image. We want to process each pixel with respect to the pixels around it. We don't want to process the pixel on its own or in the company of the entire image, right? We want to look at the pixel look at each pixel with regards to the pixels around it. That's it. So to do that, we need a new type of network. Yeah, we need a new type of network, and that is where convolutional networks come into play. So convolutional layers remedy these issues by using spatial information at each layer and not having the number of parameters scale with the size of the input data. And so convolutional layers, as you probably already know, rely on convolution, which we'll look at now in the next section or two. So convolution. And one sec. Forgot to make these slides. There we go. So, convolution, fully connected layers. For fully connected layers, we know we have a particular image here, and we know every pixel in this image is connected to every pixel in the hidden layer, right? And each of these connections has its own weight, and each of the weights could be different, right? Make sense? That's what we were doing so far with the multi-layer perceptrons. We could have locally connected layers. This is a abstraction of convolutional networks, but locally connected layers are a thing where each hidden layer is connected to each hidden perceptron is connected to a group of pixels. Okay? Is connected to a group of pixels, basically a pixel and its nearest neighbors. That's what each of these perceptrons is equal. So whereas before you basically took an image, maybe a 2D image, and you connected it to a very long vector of perceptrons. Now you take a 2D image and you connect it to probably a smaller 2D image of a 2D matrix of perceptrons, right? And this isn't a bad thing. This isn't a bad thing mainly because, at least in this case, you have different hidden elements that care about the pixel and its nearest neighbors, right? You have some relative spatial information going into the model. The bad thing, so it's not necessarily about this is somewhat of a good thing. Of course, the not so great thing is that in practice this becomes you still have a ton of weights that need to be trained. Okay, pretty much the same issue as here, except they're just less weights, right? But at least in this case, you have much less weights to train. So this is one optimization we can make. We simply say each hidden perceptron is connected to a local group of pixels. Okay? Not bad, but maybe we could do better. The better way to do it is simply to say each perceptron, we have a locally connected layer, but we say basically that each of these weights, instead of every single weight having a different value, we say that each of these weights are the same value. So for instance, the leftmost pixel for each local group has the same weight that is connected to a particular dedicated hidden perceptron. Okay? So why do we do this? Well, we do this because the number of weights, the number of trainable weights, severely gets smaller, right? That's a good thing. This allows us to basically, instead of having, what was it? 1, 2, 3. Instead of having 9 weights to train, now doing things this way, it lets us have only 3 weights to train. Okay? And it's actually kind of a good thing, right? It's kind of a logical thing because let's say we wanted to look for edges in the picture, right? So we look for an edge in the local group. We look for a particular feature, right? The red, green, and blue feature. We're looking for this feature in this local group, right? Now, when we go to another local group, why would we want to look for a different feature? We still want that feature, right? We want to find this feature in all the different local groups, right? We are effectively filtering each of these local groups and trying to find a particular feature for a particular filter. So instead of saying, okay, each of these weights is something different and we got to do all the training for each of these particular parameters, we simply say, okay, we have one filter and we pass each local group through that one filter to get some new hidden layers. And then we do that again and again to get new features. Does that make sense? So that is what a convolutional layer is. It is simply the idea that you break the image up into smaller local groups, and then you pass it through what's called a filter, right? And with this filter, all it's doing is simply looking for a feature. So let's discuss this filter is, so this is what convolution is. So let's first discuss what a convolution is and then see exactly what this does to an image. So let's first jump back and see what a convolution is. And from Wikipedia or Wikipedia, Wikipedia, there we go. We know that a convolution in mathematics, a convolution is a mathematical operation on two functions, f and g, that produces a third function, f dot g, as an integral of the product of the two functions after one is reflected about the y-axis and shifted. So what does that mean? It means that the convolution of two functions is basically you take f, then you take g, you reverse g, and then you slowly pass g through f. And whatever the area, the intersected area between those two functions is, that is your convolutional value. Okay? So there are a lot of simple convolutions that you could visualize here. But the truth is, I don't think we need to go that heavily into convolutions, because most of you have probably seen convolutions before, have hopefully seen convolutions before in ECE 210, right? Convolutions are a mainstay in signal processing. So formally, a convolution between two functions is the integral for x of tau, for h as t minus tau dt. Basically, we flip h around the y-axis, and then we integrate the function as we integrate tau over this time scale t. Okay, same as we saw in the image. So in the discrete sense, so as an example, for instance, if we have two signals, two functions, I should say, we have x, which is 2, 1, negative 3, 0, 4, and we have h, which is 1, 0, negative 1. What we do with a convolution is simply we flip h, we reverse h, basically gets negative 1, 0, 1. And then we slide h over x, we slide h over or under x, and we simply multiply the overlap of the two functions. Okay? So in this case, the convolution of x and h is simply the first step that when x and reverse h intersect, basically only the element 2 and 1 are overlap, so we get 2 here. Then h slides to the right, so making 2 and 0 overlap, that gives us 0. Making 1 and 1 overlap, that gives us 1. And so on. We do the process, we slide h to the right consistently until h and x will no longer overlap, resulting in a convolution of the two functions of 2, 1, negative 5, negative 1, 7, 0, negative 4. Okay? So used a lot in signal processing, right? Hopefully, when you guys had to suffer through Fourier transforms and all of that, this is what you did a lot, right? So this isn't new to you, but maybe in a 2D network, it might be a bit newer, but it's basically follows the same intuitive pattern. You have a it's promised I fixed this. I think it didn't. I think Google Drive failed to sync. All right. So pretty simple. Whereas before, I'm sure all of you basically calculated a convolution using a serial method before. One important thing I want to just throw out there is that you could imagine convolutions as a matrix multiplication, basically doing the same thing that you did before, except in this case, instead of having h slide, you basically have x slide. Okay, same idea. And you could do it all sorts of, and you could do, so over here, we simply, each row of quote unquote x is simply the x that overlaps with h. Okay, so for the first step, in the first instance, only the first element of x overlaps with h, so that's why it's 2, 0, 0. The blank spaces are 0 or don't cares. Then 1, 2 overlaps with h, then negative 3, 1, 2 overlaps with h, and so on and so forth, right? So doing things this way might seem inefficient. you're doing way more computations, but it's actually pretty useful if you have access to a GPU. So since modern GPUs have tensor processing units now, this actually calculating convolutions using this matrix format ends up being far faster than doing it the standard way, using the standard serial for loops and stuff. Yeah, please.
Maybe this is a dumb question, but is there any applications where, like, with this convolutional stuff, they'll use it, or they'll work in the Fourier domain?
What do you mean work in the Fourier domain?
Like, I just remember in 310, they talk, like, it was sometimes more efficient to convert, like, a filter into, like, take the Fourier transform of it.
So,
But use that FT.
so I know like with neural network stuff, there's so if you search machine learning Fourier you will get so many papers of just like Fourier principles, Fourier transformation principles applied to all different parts of like machine learning neural models. So so there are uses for it. I mean, because it's a very related thing, right? So people applied in all sorts of different, like new layers, new tokenization schemes, all sorts of things like that. That all comes into play. So yeah, I highly just go on Google Scholar, search Fourier, machine learning. You'll see a whole bunch of papers. Yeah, but good question. Yeah. All right, so throwing that out there. Moving to higher dimensions, basically, did you guys do 2D signals out of curiosity in 210? No? Okay. Yeah, I wouldn't expect it. But yeah, the idea when you have a 2D signal, a 2D convolution is largely the same as a 1D convolution. The only difference is that you have two summations, two integrations instead of a single one, and both your functions are two-dimensional instead of one-dimensional, right? So a good way to visualize this is simply you have a 2D matrix and you have a 2D filter. So what you do is you pass this filter over some part of the matrix and do an element-wise multiplication and get the final value there, okay? Like you see in the GIF. So, So 2D convolution is the same as a 1D convolution, except you shift in 2 dimensions and filter the image at each shift location. And what you get, depending on your parameters, you go from, let's say this was an image, you go from an image that is m by n to an image that is something smaller than m by n, depending on the parameters you choose. Yeah.
So why, I guess, in 1D convolution, you started and you didn't have like a full matrix?
Oh yeah, yeah.
But like, why 2D?
No, that's a good question. That's a good question. Okay, so thank you, Dominic. In the 1D case, we started off as when there was only a slight overlap, right? So really, why can't we basically take this filter and just overlap like this one corner, right? And so to have 2 by 6 and to have like a 6 element there. And the answer is you absolutely can. You absolutely can. That's what's known as padding. Basically, there's a parameter that you could set in Torch, and in Torch you could set a pad, and the pad basically surrounds your quote-unquote image with extra rows and extra columns of zeros, so that your filter could partially overlap your true image, right? Does that make sense? And the reason we don't do it is that no one really finds it useful. The only reason is that just through sheer experience, having the extra padding for whatever reason doesn't seem to provide a huge benefit. I guess just having the partial overlap doesn't give the network much information, especially over starting off at the full overlap. And like since we're not beholden to some physical truth, this is just whatever works. So you're like, well, if you're not getting any more information by having that partial overlap, you could just start from here. And the beauty of PyTorch is it'll figure it out. Yeah, but you absolutely could set a padding parameter to get that partial overlap working also. Excellent, excellent question. Yeah. Good. Yeah. So convolutional neural network. So we denote. So the size of the size of the filter does not scale with the input image size. That's important. And in practice, as far as I know, and again, I haven't seen all the networks. There are plenty of things I haven't seen. But usually the filters are pretty small, usually 3 by 3, 5 by 5. I think I've seen 9 by 9 a couple of times. But you don't get huge filters. You generally keep the filters pretty small, only on the order of single digits on each dimension. Okay, and your filter doesn't have to be square. It could be rectangular. It could be rectangular. I want to go to a code. Oh, yeah. I want to go to when you set the filter size, when you set the kernel size in PyTorch, you could set an absolute value like 3. That will give you a 3 by 3 filter. You could also give it a tuple, basically 3, 2, and it'll give you a rectangular filter that way. So your filter could be rectangular, could be square, but usually it's square. I mean, that's just, again, it's one of those things that in practice, it doesn't really make a whole lot of sense to have a rectangular filter. I mean, your images are going to be largely square, or at least like 16 by 9. Having that little extra adjustment just is not that important. Okay, but anyway, so convolutional neural networks, we write the function for the convolutional neural network the same way we wrote it for multi-layer perceptron, except now we're simply writing x star h1, pass through an activation function. That star h2 goes through another activation, et cetera, et cetera, et cetera. Okay? So even with convolutional networks, we still need an activation function, a nonlinear activation function, in between each of the layers. Okay? Still same idea, because if you don't have this activation function, it is a filter, but the filters are like a physical thing, right? So it's still like a matrix. These constant matrices will combine together to form just another constant matrix, and then you'll get a linear network again, which isn't what you want. I think that covers most of it. Actually. So figure below, just the example of a convolutional neural network. Again, remember with images, typically we have multiple input channels. So when you have a convolution, you typically define the number of channels for the convolution. And you have you stack any number of filters on top of each other to get a new feature map, and then you could combine the feature maps together using whatever you want, typically like ReLU or some other, using just like a normal just using a normal linear layer or logistic layer to get some sort of output. Okay, so that's how convolution layers work. To make, in addition, so for an example of what convolution does. So I wrote this nice little function so that we could look at some convolutions. And so, for instance, we have a picture of an adorable little golden retriever puppy, and we pass this image through a filter. And this filter, and there are different, if you look online, you will find all sorts of filters that will produce all sorts of different effects. These are kind of famous ones. So if you have a filter that's basically all ones with the middle one basically a negative large value, it 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 tries to it outputs passing an image through this filter outputs a outline of the image. It basically looks for areas where you have an edge. That's all it's doing. It's looking for areas where you have an edge. So for instance, in this cute dog, with this cute dog, the edges basically appear where his fur is super distinct, and you can see that here. It's basically capturing the lines of his fur here for the convolution. There are all sorts of other filters. I think the other one I messed around with was the raised effect. So this one, this one will take a minute because open CV image always takes a minute. Oh, there we go. Oh, wow, that's dark. That got a little demonic. But if you pass it through this filter, it looks for edges, and it basically does a weird contrast thing to the edges so that effectively the image looks a little bit more 3D. Basically, all it's doing is finding those edges and making them darker. So it's pronouncing the lines a bit. So very subtle difference, but it is a difference. So that's what convolution does. It simply highlights certain parts of the image and creates a new image. Okay, that's all the convolution layer is doing. It's looking for something and just creating something new out of it. Yeah, so feel free to mess around with that. I made you could put any image you want through this function. And use any sort of any filter. A lot of interesting. And what the filters do, like the effects get more pronounced depending on the pictures. So this outline filter is very pronounced if you're passing a comic book image through it, because there's very distinct edges in a comic book. There's less distinct edges in a picture of a puppy, but I like the picture of a puppy, so that's why I did that. Okay. Okay. So neural networks that use convolutional layers are known as convolutional neural networks. Some attributes that you should define with the convolutional neural networks. Before we were basically, all the examples I showed you were basically when the filter moves one pixel right or down at a time. You don't necessarily have to do that. For instance, if your filter is 9 by 9, it would be a bit redundant to move one at a time. You could afford to move 2 or 3 pixels at a time. You probably wouldn't lose much. So the movement of the filter through the image is what's called the stride. As Dominic expertly pointed out before, padding is when you add zeros around the image, around the input, so that you can have a partial overlap of the filter in the image. You could do it, you could not do it. Depends on your data set. Kernel size. So you could choose the size of the convolutional kernels at each layer. And again, size may be rectangular or square, but usually the choices are 3 by 3, 5 by 5, 7 by 7, that sort of thing. I don't remember when I don't think I've ever seen a rectangular filter, although it doesn't mean that it doesn't exist. Okay. Okay, and of course you could calculate for a particular input, number of channels, height, and width. For a particular image input, you could calculate the actual convolutional, the convolutional image output based off the size and the kernel size, and et cetera. Okay, so just running through, there are a couple other layers that you should be aware of that mesh well with convolutional layers. That's why you discuss them usually at once. There's this pooling layer, which is simply the idea that we want to reduce the number of pixels. We want to reduce the complexity, right? Same thing as with the multi-layer perceptron. Typically what we want to do, we go out with a huge image, like a 784 a 784 dimension input, and we want to bring it, we want to compress it. We want to keep going through multiple layers, making each layer smaller and smaller and smaller, getting to a output that is 10 values, right? And each of those 10 values is a probability that the input belongs to a particular class. We have this same desire with images, right? We want to take some big input and we want to compress them to smaller inputs. So we could do that with convolutional layers, right? If the filter is very large and the stride is large, let's say we have a 9 by 9 filter, we have a 9 pixel stride, that would compress the number of features for the next layer greatly. So that's one option. The other option is simply what's called a pooling layer, which is simply look at a local group of pixels and then output either the mean of those pixels or the max of those pixels. Those are the two major options that people use. So this is what's called pooling. Simply, it's because you're pooling a group of data together. That's where it makes sense. Hopefully that makes sense. So for instance, this example is for a 2x2 max pool operation. And you're going to use it. You're going to eventually use it because you have to go from huge input to small output. So you have to eventually do this. So once you go through a bunch of convolutional layers and you get a bunch of features, like you extract the information you need from the input, you need to just compress that input down to the output layer. That's down to the size of the output layer to make it usable. And then you have the number of classification heads. So remember, the classification heads is just the number of classes that you have to decide between, right? So in the case of fashion MNIST, the number of classes is 10. So you have to eventually get a 784 pixel image down to 10 values, right? So those are the classes. So that's the classification layer, classification heads. And so sort of a last-ditch effort to get however many features you have down to however many classifications you have. It's basically like whatever, just make it fit function. You have what's called global pooling. So before you had normal pooling, which was like pooling 2 by 2 pixel groups together. This is just pooling all the group together into 10, right? This is just pooling. You have 800 features, and you want to pool it into 10 values. You just say, all right, time to just pool 80 features together, max pool them, and put it into a particular output. Wash your hands of it, right? So you should be careful. I mean, you should design your network to slowly taper. Like, you can't just be like, oh, go from 10,000. Well, I have 10,000 features, but I really don't want to do any more layers. I'm just going to do global pool and get 10 outputs. That's not going to work super well. You should sort of design your network to not taper too suddenly. But usually that's your last layer, is a global pool layer. That's just whatever the number of features you have left. You don't want to do the math. You don't want to go through all that debugging. You just say global pool this into 10 classification heads. That takes care of that. So that's why we're mentioning it, because you'll see it very, very frequently. Okay, so summary, for example, so a common CNN structure, a common convolution neural network structure, the example that is at the end of this lecture. You start off with a particular image, a 3-channel image that has a height and weight. You have a convolutional layer. That's a 3 by 3 convolutional layer with one stride 1, pad 1, 16 output channels. Then you pass it through a ReLU activation function. You do another convolution, another activation function. You do some pooling. You go through this. You're left with some feature space that is some height and width in one channel. And then you do it again. Another convolution, larger convolution sizes, get that input smaller, more activation functions, larger convolution size, get the input even smaller, so on and so forth until you're left. And then finally, you do a global average pooling, and then finally you are left with the number of classification heads. Okay? So you have you have in Torch they give you 2D convolutions, they give you 3D convolutions, they give you 1D convolutions. These are separate functions. You do have to define them separately. I don't know if there's a unified wrapper for them, but I do know each of them have separate implementations. Okay, so before we leave, let's see an example of a small convolutional layer. So right here is an example of a convolutional neural network. We have 5 convolutional layers, and so again, convolutional layer, we simply define it when we define the actual network using the torch.nn library. So torch.nn library makes our job very, very easy. We simply define each layer. We got to actually reserve the memory for each layer. So we define the layer. For instance, we have the number of in channels. We have the number of out channels. We have a kernel size, padding, stride, and so on. And we have, again, these kernels are all square, but if you wanted a non-square kernel size, you could pass a tuple into this. You have certain number of paddings. You have certain number of strides. We're not including bias here, although you could include a bias. I don't see a bias included very often in convolutional layers, although if someone finds a paper that discusses if it's useful or not, I would be very interested, but I don't typically see it. But yeah, we define the layers, including convolutional layers, pooling layers, global pooling layers, and then simply we define the forward pass. So forward pass is simply we get an input of size x, then we pass it through the first convolutional network, pass that through the second convolutional network, then we pass that through a pooling layer, then a third convolutional layer, fourth convolutional layer, another pooling layer, fifth convolutional layer, a global pooling layer, and then the output, a classification head layer, in which case this is just the number of classes, like so. Okay? So fairly simple. You've done this all before. This is just, I mean, you know the concepts, but the good thing is you don't have to do a bunch of math. Imagine doing this in NumPy. That would not be fun. But one thing to emphasize, I want to emphasize here, is that by the numbers that we chose in that example, the total number of parameters comes out to about 60,000. Okay, so remember with the multi-layer network earlier, we came out to about 110,000 parameters. So this is considerably less. These are considerably less parameters. So convolutional network. Nope, sorry. There we go. So we could revisit the fashion MNIST data sets and simply define the convolutional neural network model, define a fashion MNIST data set. What's important here is that before we were flattening the images because the layers took in a 1D vector of pixels. Over here, the convolutional layers take a 2D vector of take a 2D matrix of 2D matrix of pixels, so we don't need to flatten the image anymore. We just simply leave the image as 2D, so that little flatten function is omitted. But otherwise, that's the only difference between this fashion MNIST data set and the one earlier. And we simply do the same thing that we did 100 different times. I think this is almost exactly copied from the earlier values. Simply calculate the indices, train the data loaders, get the model, and then pass the model and the data loaders through the training loop, and then get some plots. And if we get the plots, we find that we get our training accuracy up to 100%, and our validation accuracy roughly around 78%, right? So slightly lower than the multi-layer perceptron network, which makes sense, right? There is no free lunch in neural networks, and so we have a smaller model. At the end of the day, our model is smaller than the multi-layer network. You know, at the end of the day, more weights is almost always better. But we have a network that is almost half the size of our earlier network, and we only lose 3% accuracy. That's sort of worth it, right? Yeah, please.
I have two things. So
Yeah.
one, when you're doing the global pooling, does the outputs that you have, or I guess kind of your input into your global pooling,
Yeah.
have to be like perfectly divided into how many outputs you have? Like if you could you have like 79 and throw it into 10?
No. I mean, yeah, it doesn't have to be perfect. It'll adjust. Yeah.
And then would it be beneficial to do like convolutional neural networks for a little bit and then switch back to the other way? Because if the other way is a little more,
Yeah.
like it's a little more accurate if you, I guess, make your image a lot smaller and then go to the other way.
Yeah, so yeah, that's exactly, yeah, so it's very beneficial. So that's actually, with this network, so generally what people do is we have a bunch of convolutional layers, and then max pool, and then you have, well, I didn't do, oh, well, you have one, there's one sort of linear layer here, but a lot of people do multiple linear layers after that. And you could do multiple branches of linear layers after that, and then which comes back together. So yeah, that's what AlexNet pretty much did, right? That's basically, he started off with huge convolutional networks. He started off with not a huge one. He started off with the large convolution network, and then a bunch of linear layers, and then he got to the output. So yeah, that's exactly what you should do. And you're going to end up doing it very soon too. Yeah. Oh, anything else or no? Okay. So yeah. So again, there's the accuracy is, the validation accuracy is slightly lower, 78%. Again, so one thing that's always true, and the reason why large language models are like on the order of trillion parameters is that, you know, you could be as clever as you want, but you can't really overtake brute force. You know what I mean? Brute force is still, if you have infinite amount of time, if you have just infinite amount of time in the world, then there's really no better option than brute force, right? Just throwing wave after wave of weights at a problem. There's no better option. But the thing is, we want to be efficient, right? We want to make every parameter count. So in this case, we eliminated half the network, and we only lost 3% accuracy. That's pretty good. The other benefit that you might remember. One day, I'll enable the spell checker for Jupyter. So the other benefit is the shifted issue, right? So again, I define the shifted fashion MNIST data set. I shift it by 2 parameters. Again, I have to do it 2D because convolutional layers take a 2D image. So I had to redefine the data set. But it uses the exact same indexes, exact same test set. So if we pass this shifted data set through the convolutional neural network that was trained on the normal, that was trained on the standard MNIST data set, not the shifted data set. The model was trained on the standard MNIST data set, and all I'm doing is evaluating how much that standard CNN model, how well it performs on the shifted data set. I get an accuracy of 75%. So on the standard data, the standard model, the standard CNN gets an accuracy of 78%. When the data is shifted a bit, you get 75%. Not too bad. So what does this show you? This shows you that convolutional networks are generalized far, far better than the multi-layer perceptron that we saw earlier. And that makes sense because basically you're putting the image first through a bunch of filters that identify a bunch of features, and then you're passing it through a bunch of linear activation functions and like activation functions and layers and stuff, right? So because of that, you're really blocking the network from viewing the absolute position of an image. You're sort of giving the network some. It could probably tell roughly where a feature is, but it can't tell, oh, this center pixel is definitely white. What the network is looking at with the filters is there's an edge here, roughly in this position, and then there's another edge roughly in that position. So those two things together tell me that this thing is a pant or a jacket, right? So because of that, the whole network generalizes far better and is more robust against against like the image being shifted a little or warped in some way. Okay, so that's it for today. I promise I'll release the midterm grades today. I got delayed, but I will release it today. My office hours today will be online instead of in person. I posted the link on Piazza. Project descriptions will be posted early next week. Homework done will be posted tomorrow. And most importantly, have a good weekend. All right, thank you guys.